Welcome to today's lecture. So continue the operations research course, and we'll look at transportation problem. So let's start. So in the transportation problem, we should introduce ourselves to it, look at what it is at all, or what do we refer to as transportation problem. And also there may be a transportation problem which is balanced, and we will then solve the transportation problem, also introducing a new method called Transportation Tableau. We'll see how we can determine the optimal solution from the Transportation Tableau. And sometimes the solution or the problem is not balanced. So it's called an unbalanced transportation problem. So we'll look at what we mean by that. We'll look at the issue of degeneracy. It occurred in the simplex. So we'll see how we can also see it in the Transportation Tableau. And also some prohibited routes. So you are transporting through a route and the route is not available or is prohibited. How do you handle that? There may be multiple optimal solutions, as it was in the linear programming that we solved using the simplex or the two-phase simplex tableau method. And we'll solve a maximization transportation problem. So let's see what we have. So usually, the translation problem is a special case of a linear programming problem. That's why it was expedient that we understood what we mean by linear programming, how we can formulate it and how we can solve it, right? So usually in this case, we are dealing with transportation of a product from a number of sources or even one source with limited supplies to a number of destinations, with limited demands or specified demands or known demands. So the objective is normally to minimize the total cost of transportation. That's generally the objective when we talk about the transportation problem. So this is how it works. So usually we have a supply source or where the product is coming from, and also demand destination. So for this particular example or illustration, right, you see that we have three sources. That is 1, 2, and 3. And each source has the capability to move products from one source to destination 1, to destination 2, to destination 3, to destination 4 in that order. Again, it can move from source 2 to the various destinations or 3 to the various destinations. So if we know the various demands, right, how then do or should we, transport the material, which route is the best, and how should the distribution be done? That's how we have the transportation problem. So for a typical balanced transportation problem, right, this is what we mean when we say it's a balanced transportation problem. It means that there is a total supply equals to the total demand. So if we have 3 supplies, then we have 3 demands. We have 2 supplies, we have 2 demands. So the number of supplies or the source of supplies are equal to the total number of demands, right? Good. So it's better to treat this. Let's look at an example. So a concrete company transports concrete from 3 plants to 3 mine construction sites. So obviously from 3 sources to 3 destinations. So it's balanced. The supply capacities of the 3 plants, the demand requirement at the 3 mine construction sites, and the transportation costs are given in this table. Right. So obviously when you see this, you can see that you can easily solve this using linear programming, right? However, when you are restricted to solve with transportation problem, or however, the special case of the transportation tableau makes the solution faster and better than the simplex method. So that's why we need to look at that. So in this tableau, we have the plants. That's we have 3 plants, 1, 2, 3, and we have 3 destinations, 1, 2, 3. And we have the cost. So the cost of moving from 1 to 1 is that. From 1 to mine site 2 is that. From 1 to mine site 3 is that. From 3 to mine site 2 is 9, and 3 to 3 is that. So similarly, this is how it is, right? And the sources become the supply. So this is the amount available from each sources, and this is the demand from each for each mine site, right? So when we say it's balanced, it means that the total supply is equal to the total demand, right? Still the total demand. So that's why we say it is a balanced problem. All right. So typically when you have a transportation problem, we say that you build a network. So you build a network and you call it a network model. So the network model for this problem is said that we have source 1, which can deliver 120, or the availability of product there is 120. Source 2 is 80, and source 3 is also 80. And source 1 can move to destination 1, destination 2, destination 3, but there are various demands available or required for each destination. Therefore, how do you transport the materials, and how much should we transport it? That's what we don't know. So we use the double subscripted. So the double subscripted is the Xij here, right? Saying that let me transport from X1, from one supply to demand 1. Let me have from supply 1 to demand 2, and then from supply 1 to demand 3. So you have the various paths drawn on the network modeled, and also showing the various decision variables. How much should I move from 2 to 1? So we have X to 1, from 2 to 2, X to 2, from 2 to 3, X to 3, in that form, in that order. So repeat it also for the supply 3. So if we are to solve this, using the linear programming that we did, then we can say that we should let X1, Xij be the tons of concrete to ship from plant I to site J, right? And therefore we will be able to form, we know the various activities, 8, that's the cost of transportation. We are minimizing cost. So transportation for from supply 1 to site 1 is 8. So we form that as our objective function, right? And it will be subject to supply. We are using the equal sign because it is the total amount that is there, and everything needs to be supplied, right? So it's a binding constraint, or it's a hard constraint, let's put it that way, right? Okay, so that means that everything on the left-hand side should balance the right-hand side. So we have the 3 constraint for the supplies and that for the demand. And surely you have to satisfy the non-negativity rule, that is the Xij is greater than or equal to 0, all right? So this is typically how the linear programming works, right? However, we don't want to use this, right? So you see that in the general form of the transportation problem, right, there is M sources of M sources, or M sources of supplies or supplies, and there are also N destinations, right? N destinations. So when you look at from the linear programming model, right, you see that we have the CJs, the IJs, and the activities, right, the XIJs, the decision variables. So this has the objective function, and we have the various constraints. So the XIJs, summation of the XIJs, XIJs for the supplies from J is equal to 1 to the total number of supply N, right, will be equal to supply 1 or supply I, and the I is 1 to number of M, right? That's M supplies, and the demands will also be the decision variables that must be sent to the various destinations, which are the demands, DJs, and the J are from I1 to N. So you see that we have M sources and we have N destinations. All right, so since it is a balance problem, it means that the summation of the supply is always equal to the summation of the demands, right? So the simplest method could be used to solve this problem, but there are special solution methods which are computationally more efficient, and that is what we want to use, or that's what we want to refer to as the transportation problem. So this is how the transportation tableau is. It's also very simple, it's very simple. So we have the table, right? We have the table, and you always have where it's coming from and where it's going. So where it's coming from are the sources, and where it's going are the destinations, right? And we have the various sources. So source 1, source 2, source 3, and that order up to source M. And the various destination 1, destination 2, to the total destination N. Right. So here you create a small box within the big box, and you create this. So let's move to our whiteboard, and we'll be able to demonstrate this vividly there, or nicely there. All right. All right. So from the problem, right, we have the cement mix. We have the cement mix, which is let's say we have plants, and I just want to represent this for us to understand. Supply. So plant 1, plant 2, plant 3, destination 1, destination 2, destination 3, or something like that. So we have the destinations here. So there's the plants or the sources. So we have 8, 5, 6, 15, 10, 20, 3, 9, 10. So the total is 120, the total is 80, the total is 80, and we have 180 here. And we have our demand here, which is in tons, all right? And the total demand here is 150, we have 70, and have 60. All right, so for us to solve this problem, right, we first have to, identify obviously the initial solution, but we have to look at the kind of method that we want to use. So in the transportation tableau, right, there are several methods that we can use to solve the tableau when we have our initial solution, right? When we have our initial solution. So two main methods will be introduced in this program, and then we'll be able to, at least, there are also other methods, but we will not go with that, right? So when the number of M is equal to N, or the number of supply is equal to the number of demand, right? Then we say that the solution is, the problem is a balanced problem, right? So in a typical linear programming problem, right, the number of basic solution in the simplest tableau is equal to the number of constraints. You remember that? Good. So therefore, in the transportation problem too, one of the constraints is redundant due to the balanced conditions, right? So therefore, we see that if the number of constraints are M plus N, right? Because we have total number of supplies and total number of demands, right? So the number of constraints that must be satisfied will be m plus n minus 1, right? That's for the solution, that will be in the balance condition, right? So we'll have m plus n number of equations, but however, the number of basic solutions or the number of variables that must be in the basic solution will be m plus n minus 1. So that means that if we have a solution, if we have a problem of m plus n, number of constraints, right, then there will be m plus n minus 1 independent equations, right, and therefore the initial solution will have m plus n minus 1 basic solution, right? All right, so we'll introduce um, two methods for determining the initial solution, right? Two methods for determining the initial solution. The first one is the northwest corner method. So the northwest corner method is one, how to assign the initial solution or how to determine the initial solution. And the more technical way of determining it is also the VAM, what we call the Vogel's approximation, method, right? So we'll look at these two in finding the initial solution, right, in the transportation tableau. All right, so in the northwest corner method, all that you do is that you allocate as much, material in the, or as much, material that you are transporting in the northwest corner of the tableau so that you do not violate the supply or demand constraints within that tableau or within that box, right? And also you then determine the row 1 if all the row satisfy the amount that has been allocated satisfies the amount in the row, then it means that that row will be eliminated. Or you also assess the column to see if the column is satisfied in the demand, then you also, eliminate the column. If not, then your next allocation, right, will be the adjacent cell in the row or the column that has not been eliminated, right? So if both row and column are exhausted, then you move diagonally to the next cell. So we continue in that manner until the cell is completely, all the cells are completely allocated, right? And it will be m plus n minus 1 spaces that will be allocated, right? Great. So if you don't achieve that, we'll look at what you must do to achieve that before you move on to the iteration process. All right, so let me clean this space here so that I can use that as my tableau to solve this transportation problem. All right, so the first one we are doing is using the northwest, the NW, the northwest corner method for our initial solution allocation. Okay, so this is what we say you do. Let me use this. So you draw this. I'm sure by now you are used to drawing the simplex. Yes, will also be used to this surely. So yeah, so we have just tableau. So we have the tableau here. Yeah, and how many we have there. supply one, two, three, one, two. So this is how we draw the tableau. Let's have this. So usually we have the two here and we have the from here, right? And we have demand that our supply here. Then how many sites? We have one, two, three destinations, and we have one, two, three supplies. So I have that and have this. Then the total demand here. Total demand for one, we have it here as 150. So we can use a different color. So that is 150. Total demand here 70. Demand for mine side 3 is 60, right? The total demand for supply available here is 120. That of that is 80, and this is also 80. And because it's balanced, when you add both sides, you have 280. All right. So now within each box, you create a small box within to host the cost, to host the cost of transportation. So these are the costs of transportation, right? So we have 8, we have 5, we have $6, we have 15, 10, 12, 3, 9, and 10. All right. So what then do we have for the activity? So we said at Northwest, you allocate as much as you can. So when I move to this section or this box 1, 1, right? How much can I allocate in 1, 1, right? 1, 1. So when you look at this, the maximum you have here is 120, and the maximum you have here is also 150. So how much can you allocate? I can only allocate as much as 120 here so that it will balance the row column, right? Because you cannot put anything that will not balance any of the constraints on the right. That is the supply and the demand. So if I'm to do this well, so we'll say that we have to put as much amount that we can here, and that's we are putting 120 here, right? Then we see whether we should allocate the next row, that is row 1, 2, or the next column 2, 1, right? So when you look at 1, 2, there's nothing you can allocate here, because if you allocate any value, right, let's say that we are allocating 10 here, then the total on this row will be 130, which is bigger than the 120 that we have here. So we do not satisfy this constraint. So you cannot allocate any value there. All right, allocate any value here. So what you can allocate will be this column, this cell, which is 2, 1. And how much can you allocate? I can allocate 30. Why? Because 30 plus the 120 will give me this 150 here, right? To give the 150 here. And 30 is still lower than this 80. And so it does not conflict the constraint, which is 80, right? So you put, so you put 30 here. Then you move on to diagonal. So we now try to allocate here, right? So how much can you allocate here? I have 70 and I have 80 minus 30 is 50. So I have 70 and I have 30. So how much can I allocate so that I don't dissatisfy any of the constraints on the demands column and also the supply row? So I can allocate as much as 50. So it means that I have to allocate 50 here. I have to allocate 50 here. All right, so when you allocate 50 here, then you see that this is 120, this is 80, satisfied, right? This now becomes 150, and here is 50. You see you are still short of 20. So we'll now allocate 20 here, right? Because we cannot allocate in the X2 tray, which is this box. All right, or this cell. So the next one will be allocating in this diagonal section. So I'm coming to allocate here. How much do I have here? I have 60, and 80 minus 20 is also 60. So I can only allocate as much, which is 60. So I will allocate 60 here. So if it is balanced, you will get this, and therefore how many cells have been filled here? So we have 1, we have 1, 2, 3, 4, 5. So M is equal to 3, N is equal to 3, M minus N plus N minus 1 is equal to, okay, it's equal to 3 plus 3 minus 1, and that is 5. You know, and now many cells have been has been allocated here. We have 5. So that means that we have satisfied the M plus N minus 1. You know, so this is our initial solution, right? So how much, yeah, just trying to get rid of the thing. So I have 30 here, 50 here, 20, and 60. All right, so the initial solution here, right, will be 2,600, right? How? Because it's coming from 120 by 8, you know, plus 30 by 15 plus 50 by 10 plus 20 by 9 plus 60 by 10, and this will give you 2,600. Yeah, this will give you 2,600. All right, so this is the initial solution according to the northwest corner. Very simple, very basic, right? Very simple, very basic. So how do we then also allocate in the Vogel, using the Vogel approximation method? That is the VAM. So for the Vogel's approximation method, right, which is usually called VAM, right? The Vogel's approximation method, right? So what we do here is that in this method, we try to, you know, allocate in the minimum, you know, transportation costs within the transportation route, right? And just to maximize the transportation, you know, solution, right? So we try to allocate in the minimum cost. So what we do is that we find the penalty of not allocating in a particular cell. Then when we find that penalty, then we identify the cell with that penalty and allocate, so that we don't pay penalty for not, you know, transporting through that route or allocating in that cell, right? So we take advantage of the opportunity which exists, right? Like the cost of transporting from S1 to D3 may be the lowest, the shortest route and the cheapest route, right? So why don't we maximize that route and use it, right? However, how much can be allocated in that area? So let's try it with our transportation tableau again, right? So in this case, we will still draw our transportation tableau here, right? It's the same tableau, it's the same tableau. However, we will try to do the allocation using a different method called Vogel and not necessarily the northwest, right? So since this method is more technical, you see later that when you are iterating, the number of iteration reduces when you use the Vogel method. Okay. So trying to reduce the table a bit, right? So, all right. So we have 1, 2. Let me put this one here. Let me put this one here. And I have 1, 2, 3 supplies, 1, 2, 3 destinations. How much demand supplies available here? 120. How much available here? 80. How much available here? 80. How much demand is available here? 150. We have 70 here and we have 60. So the total is 280, which means it's balanced. So there is a cost within each cell. So we still bring this cost within the cell, and the cost is 8, 5, 6, 15, 10, 12, 3, 9, and 10. So what we do is to find the penalty, right? A penalty of not allocating, right? So this is what we do for the column, right? So we have the column penalty costs here, and we have the row penalty cost here. So what we do is that we scan through this column 1, right? And we have the various costs, 8, 15, and 3. So what is the minimum cost here, which is 3? And what is the next minimum, which is 8? So the difference is what? 5. So you write the 5 here as a penalty cost. Then we come to the second column. The minimum is 5, and the next minimum is 9. So the difference is 4. The next column is 6. The next minimum is 10, and the difference will be what? 4. Then we also have on the row, the minimum is 5, and the next is 6. So the penalty is 1. Then for row 2, the minimum is 10. The next is 12. So the penalty is 2. And for row 3, the minimum is 3, and the next is 9. So the penalty cost is 6. All right. So what you do here is that we identify the largest penalty cost here, right? And the largest penalty cost here is 6. It's 6. So that means that we have to find the cell. So the largest penalty here is 6. So what that means is that we have to allocate in that cell as much as we can. So we look at the row. So in the third row that had the 6. So we come to the third row and we identify the minimum cost here, which is this cell. So we have to allocate as much as we can in this cell, right? So how much can we allocate here? We have 80 and we have 150. So the minimum value that must be allocated to satisfy both the supply and the demand will be 80, right? It will be 80. So we have to allocate 80 in this region. We have to allocate 80 in this region. All right. All right. So when we allocate 80 here, then we go around again and calculate the column penalty cost and the row penalty cost again. So let's say 5, 4, let me just delete and rewrite them again so that we'll get more space here. 5, 4, and 4. So the next column here, we have 8 is the minimum. That's column 1. 8 is the minimum, and the next is 15. So the difference will be 7, right? For this row, the minimum is 5, and the next is 9. So the difference, now you cannot fill this area or allocate any value in this cell, right? So therefore, the minimum here is 5. For column 2 is 5, and the next minimum is 10. So 10 minus 5, the difference is 5, right? Good. Now we have 6 and we have 12. So the difference will be 12 minus 6. When we come to the column, the row penalty, right? We have the minimum, which is 5, and the next minimum is 6. So the difference is 1. For row 2, the minimum is 10. The next minimum is 12. The difference is 2. All right, so here we find the largest penalty cost. The largest penalty cost is 7. So we go to that column, 7, and we find the minimum cost here. And the minimum cost here is cell 1, which is 8. So we allocate as much as we can, just not to conflict the constraints for the supply and that for the demand. So the total amount that can be allocated here will be 70. Why? Because 70 plus 80 on the column will give us 150. And 70 is less than 120 on the row. So 70 is the largest minimum value that can be allocated here, right? So with this, you can see that nothing can be allocated in this column. So you take it out, right? Usually you take it out. You don't cancel it as I'm doing, right? This is just for illustration purposes. So you don't cancel it as I'm doing, but you take it out using, take it out like that. So you calculate for that column again, right? So we took the row 3 out, and now we're taking the column 1 out. All right, so what we do again is that we go around again and calculate the penalty cost for the various available cells. So the column 2 is available now. The minimum is 5. The next minimum is 10. So the difference is 5. Column 3, the minimum is 6. The next minimum is 12. So the difference is 6. Row 1, the minimum is 5. The next minimum is 6. So the penalty cost is 1. Row 2, the minimum is 10. The next minimum is 12. So the penalty cost is 2. So at this section, what is the largest penalty cost here? That is 6. Means that we have to allocate in 6. right? So we come to column 3 and we find the lowest cost, which is 6, right? That is this region. So how much can we allocate here so that we satisfy this 120 and we also satisfy this 60, right? So if I'm to allocate 60 here, then it will be 60 plus 70, that will be 130, and 130 will not satisfy or will be greater than the 120. It will not satisfy, right? So then we have to allocate the difference that will satisfy the row 120, right? And also satisfy the column 60 demand, which is the column 3. So the value here, it will be 50. That means that 70 plus 50 is 120, right? And 60 is still below that. So here you see that technically this row leaves the penalty, right? So now we have only row 2 and 10 and 12. The difference is 2. So now we allocate in the minimum amount, the minimum cell here, which is the 10, right? We allocate here. So how much can be allocated here? We can allocate, we have 80 on the supply and we have 70 here. So we can only allocate as much, which is 70, so that will satisfy the column constraint, which is 70, and also the row constraint, which is 80, right? Good. So 70 must be assigned here, right? So at this point, I can take off all these lines that were serving as guide, right? And see how many cells have been allocated. I have 1, 2, 3, 4. 4 cells. How many cells needs to be allocated? M plus N minus 1. That is 3 plus 3 minus 1. That is 5. But when I counted, I've allocated 4. So it means that one more is missing to satisfy the constraints M plus N minus 1 in the initial solution. So when I look at this, obviously, I will see that the row column, right, this row column 80 needs to fill here, that is 10. And when we do this 10, right, then 70 plus 10 is 80, 50 plus 10 is 60. And therefore, we have satisfied the constraints, right? Or the condition M plus N minus 1. All right, so if we are to calculate the initial tableau, the solution of the initial tableau, we'll see that we're going to have 70 by 8 plus 50 by 6. This is 5. Plus 70 by 10 plus 10 by 12 plus 80 by 3. Yeah, that's it. And this will give us 1920. Right. So you see that using the Vogels, the minimum cost is 1920. However, using the northwest corner, the minimum is 2600, right? And we said that the Vogel, we are using penalty cost, and therefore it pushes us closer to the optimal solution. So the number of iterations that we'll do after the initial solution, is obtained, will reduce when we use the northwest and also when we use the Vogel, right? So here we'll end today's lecture here or for this lecture. And the next lecture will look at how to determine the optimal solution. So we'll look at two methods of determining the optimal solution. That is the stepping stone method and the modified distribution method. All right, so thank you for being with me, and we hope to see you again in the next lecture. Bye.